Okay, to start, problem X. We are given a vapor compression cycle using 134A as the working fluid. The states given, we're given pressure 3 is equal to 180 psi. Our temperature inlet is 40 degrees Fahrenheit. Q in, our refrigeration capacity is 10,000 tons, which is quite a bit. And our compressor efficiency is 0.75. We assume perfect condenser and evaporator, which means there's no pressure drop, and an adiabatic compressor, as well as a valve. So we are asked to find the mass flow of the refrigerant using what we were given. We need to find the power to run the compressor, and we also need to find the coefficient of performance of this cycle. So, to start, we will start by evaluating each state 1, 2, and 3, and 4, and find out what we need to know using what we already know. And from there, we can apply our equations for the vapor compression cycle using our change in enthalpies to find our mass flow and our power for the compressor and those sorts of things. So, to start. Alright, we'll start with state 1 here. State 1, we know this is 40 degrees. So, from here, since we know that our temperature is this, and that is a saturated vapor, because of this point on this line right here, the saturation line. Since it's a saturated vapor, and we know the temperature, we can use these two to find that H1 is approximately Hg at 40 degrees. So using our table, for our temperature table for our R134A, we can find the H1 is 107.39 BTUs per pound. Okay. We also will take use in knowing that S1, found the same way as SG, is 0.2189. Sorry for those. Spacing that is in BTUs per pound Rankine. Alright, on to state 2. That's all we need from state 1. State 2, we know that P2 is also equal to P3 from our constant pressure line in our diagram, and the fact that there's no pressure drop across the condenser. Okay, so we use that. So now P2 is equal to 180 psi as well. And we use that. And S2. We know S2 is equal to S1 for the isentropic compression, which is equal to 0.2189 BTU. Same units. Oh, sorry, multiplication there. But to show that on the graph, we go straight up from state 1 to state 2s. So that's actually 2s, I apologize. So, we can use that to interpolate and find H2s. So using that, we go to our superheated vapor table of 134A, and we can interpolate between the values of entropy and enthalpy. And so you can bang this out on a calculator, of course. I'll just do it by hand. It's a 4. So we're just found our two values. We know our we know S2 is right in between these values, so we have to interpolate. So 123.21, just getting these all from the tables. At 180 psi, of course, 2166 minus 0.2189 over 117.41 minus H2S in this case, because we went straight up and assumed an isentropic compressor. So there's no change in entropy, which of course we will fix later when we use the efficiency of the compressor. So we can bang this out, find that H2S is equal to, of course, right in between M of 118.77, also in BTUs per pound. Okay. From here, we correct this and find our H2 that we need using the equation of our efficiency is equal to H2S minus H1 over H2 minus H1. So we can rearrange this and get H2 is equal to H1 plus the value of H2S minus H1 over the efficiency. So if we want to bang that out, 107.39, so plus, and then what we just found, 118.77 minus 107.39 over our efficiency of our compressor is all equal to H2, which is equal to, as we expected, a little higher, 122.565. Alrighty. So we found our H2. We found our H1. So we can continue on to step 3. Sorry, state 3. We'll bring that down here a little bit. State 3, we know that P2 is equal to P3, which is equal to 100 psi from our no change in pressure. And we also know, going back to our diagram, that this time is a saturated liquid, which helps us tremendously, makes this much easier. So we can do the same thing as in step 1 up here. We know using that, and it's a saturated liquid, we can find out that H3 is approximately HF, which is equal to 50.64 BTUs per pound. Okay, that's great. On to state 4. Using what we know about throttles and expansion valves, we know that H3 is equal to H4. We know that there's no change in enthalpy across our throttle. So we know that H3 is equal to 50.64, which is also equal to H4. So now that we have H3, H2, H4, and H1, we can go ahead and apply what we know about the vapor compression cycle to find out what we want to know. So I'll go ahead and start a new page here, just so it's nice and clean. Just lined up. So part A, we want to find the mass flow of refrigerant, m dot. Okay, using what we know and what we already have, we know Q in, our refrigeration capacity, is 10,000 tons. And we also know that Q in is equal to m dot, and the change in entropy times the change in entropy across our evaporator. So, rearranging this, we get m dot is equal to Qn over H1 minus H4. We know this and we know this. We're just going to have to do a quick conversion. So we're going to do 10,000 tons. So our units line up, of course. Is this equal to 200 BTUs per minute per ton? We're going to have to multiply 1 minute. A minute is 60 seconds. So we can do all of that. That's Qn right here over H1 minus H4. H1 minus H4 is 107.39, found in our first step. And this is 50.64, found in our third and fourth step. So we can calculate that. M dot comes out to be 587, I think. Yep, 0.37, and when our units cancel out, that is in pounds per second. That's what we're looking for, our mass flow of our 134A. On to part B. We are looking for the power of the compressor to keep this vapor compression cycle going. So, we know that this, from our vapor compression cycle, is just equal to m dot times the change in entropy across our compressor, as you can see in the figure. So, we'll just plug in what we know and what we've already found. Of course, 587.37. H2 minus H1. Remember, we found our H2 using our compressor efficiency. Of course, minus 107.39. And that comes out to be with a pretty large mass flow rate, of course, because of our large refrigeration capacity. We're going to need quite a bit of power, which comes out to 8,193.34 BTUs per second, which is quite a bit. Alright, and then part C, bringing it all together. We know that beta, our coefficient of performance, is always our desired effect over our costs. In this case, it's the work of our compressor to run our cycle. So using this, we know that our desired effect is our cooling, and our cost is the work of our compressor. So this comes out to be beta is equal to m dot H1 minus H4 m dot H2 minus H1. Of course, these cancel. We already know these values. We'll just plug them right back in to make it clean, we can see it again. Bring it down here so you can see it. 0.39 minus 50.64 over 122.565 minus 107.39. And when we calculate that, we get our coefficient of performance, beta, equal to 3.74.